Thank you, Mark. So, hello everyone. I am Varinder Singh. So, currently I am a postdoctoral fellow at Center for Critical Physics of Complex System, Institute for Basic Science in South Korea. So, today I am going to talk about my recent work on thermodynamic uncertainty relations in major heat engines. So, this work is done with collaboration with Vahid Shagaki, who was a PhD student in University of Ansubria, and Professor Ozgur, who is a professor at University Turkey, and Dario Rosa, who is a junior team leader at PCS IBS. So first of all, I want to thank the organizers for giving me this opportunity to present in my work on this platform. So now let me start with the second law of thermodynamics. So second law of thermodynamics deals with the notion of irreversibility. So irreversibility is quantified by entropy production. So although there are many definitions of second law of thermodynamics, but I will talk about which involves entropy in its definition. So there are two equivalent definitions. First one is for isolated systems. So entropy of a thermally isolated system never decreases. So del S should be greater than equal to 0. And if the system is interacting with some reservoir or some other system, then its entropy can decrease. So there is another statement, equivalent statement. So we can say for the total system, the entropy of the total system always increases under any irreversible thermodynamic change. So total system, total entropy means entropy of the system plus entropy of the environment. So it should be greater than 0. The special thing about second law of thermodynamics is that it do not possess time reversal symmetry. So it puts constraints on what thermodynamic processes are allowed in nature. And the answer is that those that increase entropy. So the examples are naturally heat flows from hotter body to a colder body. And the second one is free expansion of a gas into vacuum or diffusion. Like if you put a drop of water drop of ink into the water, it will spread out throughout the body of the water. And then chemical reactions, they are also irreversible. Like if you put a piece of sodium into the water, there will be explosion due to the chemical reaction. And this second law of thermodynamics, it is statistical law. So although I said that the natural direction of events is that in which entropy increases, but there might be rate of fluctuations in which entropy might decrease. But probability for those events are very, very low, such that practically they never happen. So what second law of thermodynamics, it can be defined in a more defined way. So here is the expression in change in entropy of a system which is in contact with heat and particle reservoirs. Like so del S is equal to del S exchange plus sigma. So this quantity del X exchange is the entropy change due to exchange of heat and matter with the surrounding. And like in case of thermal reservoir only, so this will take the form Q upon T, where T is the temperature, Q is the heat exchange between the system and the reservoir. And sigma is the entropy produced by the irreversible process within the system. So here, and this entropy is produced during the transformation, spontaneously produced during the transformation. So modern formulation of second law of thermodynamics says that entropy production should be greater than 0 in any thermodynamic process. So now this second law of thermodynamics just states that in the irreversible processes sigma should be greater than 0. But do we have any generalization of second law of thermodynamics? Do we have any stronger statement on entropy production? So I will come to that point. But before that, I would like to discuss another aspect of second law of thermodynamics. So back in 1824, a French engineer Carnot, he introduced the concept of Carnot efficiency. So actually Carnot cycle is a reversible cycle which operates between two thermal reservoirs. The special thing is that the efficiency of such a reversible engine is given by this formula, eta is equal to 1 minus Tc by Th, and it is a universal formula since it doesn't depend on the parameters of the system. It just depends on the ratio of reservoir temperatures. It puts an theoretical upper bound on the efficiency of all macroscopic heat engines working between two thermal reservoirs. But Carnot engine is not practical one. Although it operates at maximum efficiency, but it has vanishing power output because it takes infinite time to complete one cycle. So total power which will be work upon time, it will be zero. So real heat engines should work in finite time with finite interrupt production, and they should produce finite power. So finite time thermodynamics deals with these questions. So irreversible heat engines which operates at finite power output, they also produce finite entropy productions. So that's why their efficiency is not Carnot efficiency, it will be less than the Carnot efficiency because of the entropy production. So it has been seen that there is a trade-off between efficiency and power in all engines operating in finite time. So this is the general curve. So we can see that there is a certain point at which efficient power is maximum. So this is efficiency at maximum power, and from this figure it is clear that this region right to this vertical line, we should operate our heat engine in this region. Now, what are the most desirable features of a heat engine? So the question is whether a heat engine can beat trade-off between efficiency and power, and more important, so whether a heat engine can operate at finite power with maximum Carnot efficiency. So the answer to these questions and the question I posed earlier, whether there is stronger statement of second law of thermodynamics, is yes. And now let me come to thermodynamic uncertainty relations. So actually thermodynamic uncertainty relations, they are relevant for nanoscale heat engines, as nanoscale heat engines are subjected to strong fluctuations which will affect their performance and their precision. But also, as I just mentioned, that if we want finite power from heat engines, then there is also associated entropy production. So thermodynamic uncertainty relations, they represent a trade-off between the entropy production rate and relative power fluctuations in heat engines. Actually, thermodynamic uncertainty relations, they are not linked to the power fluctuations. It is valid for any current. But since I am talking about heat engines, so power will be, I will talk about the power fluctuations. And these relations were discovered for biomolecular processes back in 2015 by Seifert, Barato and Seifert, and eventually proved by using the formalism of large deviation theory. The interesting thing is that this inequality, it has like certain implications for the case of heat engines. So this inequality can be translated to the following inequality. So as I asked the question, like whether there is a stronger statement of second law of thermodynamics, so the answer is yes. First, you can see this inequality. This gives a trade-off between entropy production and relative fluctuations. So it gives more information than the second law of thermodynamics for nanoscale systems. And again, the other question was that engines can operate at finite power with Carnot efficiency. So from this inequality, we see that if efficiency of engine, if we put efficiency of engine equal to Carnot efficiency, then for this, like in order to satisfy this inequality, power, because this will become zero, then power fluctuations in power, it should diverge. So engines can operate at finite power with Carnot efficiency, but at the cost of diverging power fluctuations. So again, this is not useful heat engine. So now I will talk about thermodynamic uncertainty relations in a specific model of heat engines, which is 3-level laser or 3-level laser heat engine. So interesting, this is the first model of heat engine which was introduced back in 1915 by Scoville and his co-workers. And in that work, they show that they mapped a laser to a heat engine, and they showed that efficiency of a laser is also limited by the Carnot efficiency. So here, this is the scheme for a 3-level laser heat engine. So in order, let me explain its operation. So in 3-level laser heat engine, so level G and level 1, they are connected to the hot reservoir, and level G and level Z0, they are connected to the cold reservoir. So by actually varying the temperature of these reservoirs and the frequency gaps, so sorry, they should be omega C. So we can obtain population inversion between level 1 and 0, because for laser action we need population inversion between two certain levels. So once we obtain the population inversion, So if we shine a electromagnetic light on it, then it will stimulate the transitions of electrons from upper level to lower level, and because of the stimulated emission, the emitted photon or electromagnetic waves, they will be in phase with the incoming waves. So it will amplify the incoming signal. So this is the working of three-level measure heat engine. So basically, the transition by the hot reservoir, it will raise the system from level G to level 1. Then by the stimulated emission of radiation, it will be brought back to the level 0, and then cold reservoir will brought back the system to the ground level. So in this case, this is a free Hamiltonian, and this is the matter field, like matter here, matter is like three-level system, and field is electromagnetic field, so which is in resonance with these two levels, 1 and 0. So here I am taking the classical electromagnetic field, not the quantum version. So and the overall dynamics will be given by this master equation, where LH, rho and LC, rho are the Lindblad dissipators. So here I will discuss two different configurations of three-level measure. So first one is this, in which like this is hot reservoir connected to these levels and cold reservoir connected to these levels. And the another configuration, hot level is connected to these reservoirs, these levels same, but cold reservoir is connected to these two upper levels. Although these both models known as SSD model after Spugel's name, but actually they don't perform. As far as thermodynamic uncertainty relations are concerned, they are different. So these are the main relations when this Q1 and Q2 are actually, sorry I have not mentioned it, this left hand quantity, I am calling it Q1, TUR ratio basically. So we have evaluated these thermodynamic uncertainty relations, or this TUR ratio, for both models 1 and 2 using the full computing statistics. So here are the results. So we can see that for other parameters fixed, and when we vary the strength of the electromagnetic field, and on the y-axis we plot TUR ratio. So we can see that model 2, which one is this one? I will call this model 2, this one is model 1. Model 2 outperforms model 1 for lower values of lambda, but higher values of lambda, model 1 is better. You can obtain better precision for model 1 as compared to the model 2. But as far as minimum value of TUR ratio is concerned, model 2 is better than the model 1. So these models are not, they don't yield the same TUR ratio. But in the high temperature limit, when we ignore the spontaneous emission, because these configurations are different, because there is an asymmetry due to spontaneous emission terms. So if we ignore spontaneous emission as in the high temperature limit, so in the like Lindblad equation has formed like gamma h nh plus 1, where nh is the number of photons in the hot reservoir. So then you can ignore 1 as compared with nh. So you can ignore basically spontaneous emission as compared to the stimulated emission. Then both models yield same result. So this is the expression for that result. So when you ignore spontaneous emission, you will have the same result for TUR ratio. And interestingly, in the high temperature limit, although this is known as classical limit, but not always. So in high temperature limit, TQHT will always be smaller than 2, because as we can see from this equation, NH is number of photons in hot reservoir, number of photons in cold reservoir. So and all these things are coupling constants. So all the quantities involved in this equations are positive, and this is NH minus NC square. This is also positive. That's why TUR will always be smaller than 2 in the high temperature limit. It might be due to, because in high temperature limit we are ignoring the spontaneous emission. So when you ignore spontaneous emission, so spontaneous emission is a kind of quantum noise. So maybe because of ignoring this quantum noise, we can get better precision. So now I will discuss a bit more complicated structure. So instead of discussing 3-level system, I will discuss a 4-level system. So in this 4-level laser, so levels 1 and level 2, they are degenerate. So because they are degenerate, because of the degeneracy, when you write the Lindblad-Master equation, there will be certain cross terms. So this is the form of the Lindblad-Master equation for the 4-level system. So as if you don't have degeneracy in the system, then we will not have these cross terms. We will only have the terms which have like AK row, AK dagger, like A1 row, A1 dagger, or A2 row, A2 dagger, where A1 and A2 are jump operators. So in the presence of degeneracy, the Master equation is modified, and then even in the absence of driving, coherences and populations are coupled. Because in 3-level system, if you don't apply any drive, so you will see that coherences and populations, they are decoupled. But in case of 4-level system, because of the degenerate structure, so coherences and populations, they will be coupled, and it has certain implications on the performance of the heat engine. So now, actually these are cross terms. We will call this like gamma cos theta, gamma sin theta, and cross terms because A1 row, A2 dagger, we have this mixing of jump operators. So because this actually cos theta, this arises physically. This arises due to the interference effect between two different channels. So suppose there is a decay from level 2 to G or level 1 to G. So there are two paths for that decay. But since these paths are indistinguishable, so that's why you have to sum their amplitude and square. I mean to say, because these paths are indistinguishable, so there will be interference effects in between them. So these terms specify that interference terms. So now usually in case of atoms, all transitions, we usually consider dipole transitions. So these are, so there will be dipole moment associated with one transition 2 to G, and again for 1 to G. So this P is an angle between these two transitions. So P equal to cos theta, which is the angle between these dipole transitions. So it can take value from P equal to -1 to 1. So if there is a completely destructive interference, like completely, if dipoles are anti-aligned, then P equal to -1, and if for constructive interference, if dipoles are aligned, then P equal to 1, and P can take any value. So even the physical reason, there might be another, like we can explain in another way as well, why coherence is happening. So it is like that, there is a transition from level 1 to G, and then same photon will be absorbed by this transition from G to 2, and it will create a coherence between level 1 and 2. So there will be terms like rho 1, 2, which coherence can be manipulated by manipulating this angle between these two dipole transitions. So now, what is the effect of noise-induced coherence? Although from its name, noise-induced coherence, it looks like that it will always be, you can say, harmful for the performance of heat engine, but it is not the case. So in this case, actually, when I am talking about the noise-induced coherence, I am just comparing model 1 to this degenerate measure heat engine. So from these graphs, we can see that like these graphs are for like TUR ratios for 3-level model and then for 4-level model. So this solid curve corresponds to the 3-level model, and all other curves correspond to the 4-level laser heat engine with noise-induced coherence. So, but the difference is that for different cases, we have set the value of noise-induced coherence parameter P different values. So this is P equal to, like this curve is for P equal to -0.945, this is for P equal to 0, and this curve is P equal to 0.7. So we see that in case of the destructive interference, when dipoles are anti-aligned, this curve, this TUR ratio outperforms the 3-level system. So as far as the TUR is concerned, like you can suppress the power fluctuations as compared to the 3-level system. So noise-induced coherence can be used as a resource to suppress the power fluctuations in heat engines. But again, in certain cases when P is positive, this has, like you can say, it has higher TUR ratio. This means that in this case, power fluctuations are amplified. So depending upon the parameter region, you have to select a certain value so that you can use it as a resource. And then here I have plotted this TUR ratio with respect to the noise-induced coherence parameter P. So as we can see that all these curves exhibit a certain minima at certain value of P. Certain value of P. So here these three terms correspond to the different driving strength. We can do the same thing with, we can fix any other parameter like NH, NC, number of photons in the hot and cold reservoir, or we can fix system work coupling constant gamma H and gamma C. The results are almost same. Then now there are few nice observations. So first one is that 4E4 completely destructive interference when P equal to -1. So we have an analytical expression for the TUR ratio which is given by this. And in this case, this only depends on the reservoir number of photons in the reservoirs. It doesn't depend on the system parameters. So in this case, it is always greater than 2. So if you want to violate, and okay, just I forgot to highlight one important thing, that in both cases, like these heat engines, they always violate the classical TUR. They can always violate classical TUR. So in this case, we see that depending upon like value of P and lambda, they can violate classical TUR or they cannot violate. We have to select smartly. Okay. So it should be greater than 2. And then another observation is that in the high temperature limit, independent of the all parameters, this TUR ratio with noise-induced coherence is equal to 2. So in general, in high temperature limit, it performs, like you can say, worse than as compared to the 3-level counterpart. Because in case of 3-level system, this TUR ratio was always smaller than 2. And another observation is that QNIC, this TUR ratio diverges for the completely constructive interference. So this is interesting because there was a paper back in 2011 by Scully and co-authors. They showed that you can double the power of a heat engine for with this noise-induced coherence when you compare 3-level and 4-level system. And in their case, you can double the power for P equal to 1. But as I have shown that there is another quantity you need to consider, which is power fluctuations. And power fluctuations, they diverge at P equal to 1. So we should not operate our engine at P equal to 1, but at a smaller value. And then finally, we have also plotted histogram for sampled values of like all three models of heat engines. I discussed Q1, Q2 and Q3 for random sampling over a region of parameter space. So as you can see from these histograms, so in the inset I have plotted the TUR violations, which is always smaller than 2. So as you can see that in model 1, the minimum value is around 1.96. In model 2, minimum value is right 1.62, and with the noise-induced coherence, the minimum value is around 1.99 something. So this means that if you randomly choose any value of noise-induced coherence, then most likely it will enhance the power fluctuations in heat engines. But if you choose it smartly, then you can use it as a source to suppress the power fluctuations. So here are the conclusions. So classical TUR relations can be violated in 3-level major heat engines. So in these violations, spontaneous emission plays an important role in the degree of violations of classical TURs. As in the absence of the spontaneous emission, model 1 and model 2 discussed here yield the same TUR. Again, in the high temperature limit, classical TUR is always violated for 3-level major heat engine, and it is because here you are ignoring spontaneous emission and quantum noise. And the final message, depending on the parametric regime of operation, the phenomenon of noise-induced coherence can either amplify or suppress the relative power fluctuation. But we would like to suppress the relative power fluctuations. So we would have to select that regime. And there is future outlook. So here we have just calculated the TURs, but we cannot exactly quantify the role of coherence. So, but we can calculate it as well. So there is a recent paper by Saito. So by using that, we can calculate the contribution of coherence in the violation of the standard TUR. and then this can be done by going steady state, beyond steady state, and using quantum trajectory approach. Okay, thank you. That's all.
Thank you very much, Varinder. Do we have any questions in the room?
Yeah, thanks, Varinder. So, for almost all of the plots you showed, the TUR ratio was actually very close to 2. I mean, I think apart from the slide you just skipped over, basically the TUR ratio was within a few percent, was just 2 for all parameters and all models, right? So do you have any intuition as to why these models actually get so close to the classical TUR bound, which is often an extremely loose bound, right, in larger systems, but many systems, right? It's often one's very far away. Here you're almost exactly at the classical bound, notwithstanding any kind of violations. So do you know why?
Yeah, I guess so, because apart from this histogram, values of Q are quite close to 2. And even so, we have intuition from these results, because in the high temperature limit it is equal to 2, and even in the case of like in the case of 3-level system, it is quite close to 2, although smaller than 2, quite close to 2. So I think it might be related to the second order coherence function. Okay, because as you can see that if you write your power spectrum, or like you can say power spectrum, so for this when you operate in the high temperature limit, this light is like thermal light, so that coherence function is also close to 2, second order coherence function. So that's why when you are operating with reservoirs with high temperatures, then it should be directly proportional to the second order coherence function. So we have this explanation for this.
Okay, but in a maser, wouldn't you expect the second order coherence function to be close to 1 above threshold? I mean, if it's producing a coherent state, then
no, actually, because it was back shown by Scully in 2011 that when you go beyond certain temperatures, then your maser heat engine, it doesn't remain actually, the output doesn't remain coherent. It behaves like thermally.
yeah, okay.
So I mean to say, in beyond certain critical temperatures, this heat engine is not a good, you can say, heat engine. It cannot convert incoherent heat into the coherent output. This is a limitation.